Welcome to the wonderful world of astronomy. This is Chapter 5, Light and Matter, and this video is Part 5, Molecules and Phases of Matter. In the last video, we looked at the structure of atoms, and now we're going to look at how atoms combine to make larger things. Atoms combine to make molecules. A molecule consists of two or more atoms that are joined together. And an example is water. Now, water is known as H2O, and the reason is because it has, in a water molecule, two atoms of hydrogen and one atom of oxygen. So the little number that's down and to the right, that subscript after the H, the 2, that refers to how many atoms there are in that molecule. You notice there's no subscript after the O, and if there's no number after it, that just means 1. So if there's only one atom of oxygen, they're not going to write the 1, they just leave it alone. This is, on the right, the basic shape of a water molecule, the oxygen and then the two hydrogen atoms going off like that. If we want to get more specific, in the water molecule, here's the oxygen. And the oxygen has the electrons that orbit around it in different orbits, and the hydrogen has the electrons that orbit around it. And notice that they share electrons. So between these two down here and these two up there, it's hard to tell which one belongs to the hydrogen and which electrons belong to the oxygen. Among those, well, they're sharing them. And it's the sharing of the electrons that bonds them together. So we have an H2O molecule, or a molecule of water. Another example that you'll need to know for this class is carbon dioxide. Carbon dioxide is what we breathe out. We inhale and we breathe in oxygen. Our bodies make use of that, and then we exhale carbon dioxide. And plants need carbon dioxide for photosynthesis. This is what a carbon dioxide molecule looks like. Notice it's not at an angle like a water molecule, but it's linear. So CO2, carbon dioxide. Notice it's got no subscript after the C, so that just means one atom of carbon and then two atoms of oxygen. Another one you'll need to know for astronomy class is ammonia. Ammonia is NH3, so that's one nitrogen atom and three hydrogen atoms. And one more that often appears in the atmospheres of some planets is CH4. So CH4 is methane, one atom of carbon and four atoms of hydrogen. Some simpler molecules, but these are ones that come up a lot in astronomy. They come up as we talk about the atmospheres of planets and in nebulae, which are clouds of gas that are out there in space. Notice each one of these only has one element. So H2, molecular hydrogen. It's a hydrogen and another hydrogen bound to each other. And it would look something like this structure that you see to the right. So molecular hydrogen. As opposed to if we talk about atomic hydrogen, we can have clouds of atomic hydrogen, and that just means they're single hydrogen atoms. But when we say molecular hydrogen, that means hydrogen that's bonded into these molecules, so H2. We also have molecular nitrogen and molecular oxygen, N2 and O2. In the air that's around you, we say that our Earth's atmosphere is mostly composed of nitrogen and then secondarily oxygen. And this nitrogen and oxygen, they are not in atomic form, but rather they are in molecular form. So every breath that you take, most of what you're taking in is molecular nitrogen, N2, and then molecular oxygen. Here is a list of the molecules that you will need to remember to be successful in astronomy class. So just 5 plus the 3 that are the single elements. So we have water, which is H2O, carbon monoxide. Now, notice the difference between carbon monoxide and carbon dioxide. Carbon monoxide is just one carbon and one oxygen, and that is poisonous to us. carbon dioxide, ammonia, and methane, and then molecular hydrogen, molecular nitrogen, and molecular oxygen. So take some time to make sure you have those and their chemical symbols memorized. This is not important for astronomy, but just to show you there are more complex molecules out there than the relatively simple ones that you need to know for astronomy. And so we think about different medicines that are out there. This is commonly known as ibuprofen. It's C13H18O2, and that will not come up on the test. But just so you can see, it's a combination of carbon, hydrogen, oxygen. But it's not just carbon, hydrogen, oxygen randomly thrown together. It must be in those specific ratios. So 13 carbons, 18 hydrogens, and 2 oxygens. And this is a diagram of its structure. And that's ibuprofen, a common pain medicine. Another common pain medicine is Tylenol, otherwise known as acetaminophen. And this is C8H8NO2. So 8 carbons, 8 hydrogens, 1 nitrogen, and 2 oxygens. Caffeine we find in coffee. And by the way, it is also known as a pain medicine. It is C8H10N4O2, and I want you to be able to read a formula like this, not to have this memorized, but when you read something like that, to know what it means. It means it's a molecule that consists of 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. And some people with their caffeine like to put in sugar. C6H12O6, particularly the glucose form of sugar. Again, another combination. You notice these last few that I've been showing you, the ibuprofen, the acetaminophen, the caffeine, and the sugar, were all combinations of the same 3 or 4 elements: carbon, hydrogen, nitrogen, and oxygen. And so when you're out looking for medicine, particularly looking at pain medicine here, this is Excedrin, but you look in the list of active ingredients and you see things like this, acetaminophen, so you know it contains 250 milligrams of that molecule that I showed you. It's also got aspirin, which is another molecule. It's also got caffeine, 65 milligrams of it, which is, as I said, often used as a pain medicine. And it's that molecule that I showed you on the earlier slide. Let's talk now about phases of matter. Since elementary school, you should have been familiar with the basic phases of matter: solid, liquid, and gas. And when you think about water, the solid would be ice, and then it melts and it becomes liquid, and that's water. And then if we boil it, it becomes steam or water vapor, that's gas. Now, most often we can recognize when we have a substance in front of us, we can recognize it as a solid, liquid, and gas. So the tabletop feels solid, and we pretty much agree that that's a solid. And you see a drink, you see coffee or water or whatever, and you recognize that visually as a liquid. And then the air in the room, you recognize that as a gas. But there are more precise definitions of these phases of matter. These phases of matter are defined by how the molecules are bonded to each other, how tightly they're bonded to each other. So phases of the same material behave differently because of differences in chemical bonds. And here we have on the left-hand side of the screen, solid. So a solid is a substance where the molecules are tightly bound to each other in a rigid structure. And that's what gives a solid its rigidity. They are bound to each other. Now, if you add heat, it will give energy to those molecules, and they will, in increasing their thermal energy, remember what thermal energy is. The idea is that these molecules have kinetic energy, and they will start vibrating faster and faster. They move more furiously till they break those bonds apart. And when they break the bonds, they break that solid structure, and then you have a liquid. Now, they still have a little bit of bonding to each other. Think of those molecules as being temporarily loosely bound to each other. So these water molecules don't jump up into the air. Well, some of them do. That's what evaporation is. But for the most part, when you've got a cup of water, those water molecules, they just kind of stay put. The water stays in the shape of the container down at the bottom if gravity's pulling it down. And so that's what a liquid is. But you heat it up enough, and now we're talking about boiling the water, and whatever loose temporary bonds there were between the water molecules are completely broken. And now the water molecules just fly out into the room, and there you have water vapor. And by the way, you don't have to heat it up that much to turn the water into water vapor. In fact, evaporation, if you take a cup of water and just leave it sitting on the counter, leaving it for many days just sitting out there, the water level will start to go down. And that's because on the top of the water, some of the water molecules do have enough kinetic energy to break free, to jump out of the cup and go into the air in the room. That's what evaporation is. Now let's look more intently at what happens to matter when you increase the heat. And this is going to be relevant in our study of astronomy to thinking about there are cold planets, there are hot planets, and then there are stars. Stars are very, very hot. Their surfaces are hot. And as you go deeper and deeper into a star, it gets hotter and hotter. So let's start at the bottom of this screen. Think about what happens if we take a substance, and on this screen it talks specifically about H2O water, so I'll do it in that context. And here we have a nice picture of a snowflake. Well, here we have the water in its solid structure. And notice that those water molecules, the H2O molecules, are bound to each other. The illustrator has drawn little lines between them showing that solid structure. Now we're going to increase the temperature. That's what this arrow is doing. As we go up the screen, we're going to add more heat. And as we add heat, we melt the solid into a liquid. So melting is breaking of the rigid chemical bonds that changes it from a solid into a liquid. And so here the illustrator has drawn, there are those H2O molecules, and at any given moment, some of them have bonds between them. And again, they are loose and temporary bonds. Let's increase the temperature. Let's go up the chart. We add more heat. And now you can see those molecules. They're not bonded to each other. They're moving faster. They're just going around in all different random directions. And so it says here hundreds of Kelvin. Okay, so we have the water boiling now. And what's just happened is evaporation, which is the breaking of the flexible chemical bonds, changing the liquid into a gas. And by the way, the air molecules in the room where you are, these molecules are moving around in random directions at very fast speeds. And even though a bulk of air doesn't seem to be moving unless you've got a fan blowing or something like that, the air seems to be still. But the individual molecules in the room where you're at are moving at a typical speed of about 1,000 miles per hour, just moving around in all random directions. Okay, let's go back to the chart. We've got our water vapor, and it's still in the form of molecules of H2O, but let's increase the temperature to thousands of Kelvin. So thousands of Kelvin, which is thousands of Celsius degrees as well. Now we have what's called dissociation, where there's so much energy imparted to these molecules that the atoms that are bound together in molecules, they break apart from each other. So dissociation means the molecules fall apart, the breaking of molecules into individual atoms. You notice in the picture, the illustrator has drawn an H2O molecule as the red ball being the oxygen and the two white balls being the hydrogen. Well, now they've broken apart. So now you've got a bunch of hydrogens and a bunch of oxygens moving around in all different directions. When we look at the surfaces of stars, which are thousands of kelvins, usually we don't see any molecules because those environments are too hot for molecules to exist. Now, some of the coolest stars do have molecules on their surfaces, and so we know that it's a relatively cooler star. And as we go on, as we progress, particularly more into chapter 5, we'll look at how we can tell whether there are molecules or atoms on the surfaces of stars. Let's increase the temperature even more to tens of thousands of Kelvin. Now we get to the point where there is ionization occurring. There's so much energy that the atoms themselves are being broken apart. The electrons are being stripped away from the atoms. So we have ionization, and now we have ions, tens of thousands of Kelvin. So if it gets pretty hot into the tens of thousands of kelvins, you might have singly ionized atoms, meaning one electron taken away. So if you remember back to the previous lesson, if it is helium, for example, helium, if it's neutral, since it has 2 protons, it should have 2 electrons. But then we find ourselves with singly ionized helium, meaning there's enough energy to rip away 1 electron. But then if we increase the temperature even more, then there's enough to doubly ionize the helium. So 2 protons and no electrons. So the more ionization we have, that tells us that it's a hotter environment. Well, finally, we get to hot enough, and it says millions of Kelvin. Now we're getting towards the interior of a star, where all the electrons have been stripped away. And what we're looking at now is what's called the 4th phase of matter, which is a plasma. And so a plasma is, you've got solid, liquid, and gas. Plasma is a gas that has had some or all of the electrons stripped away from the atoms. So it's a gas made of ions. And so at millions of kelvins, all of the electrons have been stripped away. So we say at that point it is a fully ionized plasma. Now, on the previous slide, I showed you at the bottom of the screen, going from solid to liquid, we call that melting. Going from liquid to gas, we call that evaporation. We can also more loosely call it boiling. But sometimes some materials, as you heat them up, go straight from solid to gas, and they bypass the liquid phase. This is what carbon dioxide does. So frozen carbon dioxide, otherwise known as dry ice, this is used for sometimes for maybe Halloween decorations, sometimes at concerts like you see here to have that smoky effect. It's dry ice. So it is frozen carbon dioxide. It's a white brick, very cold brick of solid carbon dioxide. And when exposed to the warmer air, it doesn't melt. It just boils. It just evaporates. And we call that process sublimation, when something goes straight from solid to gas. Now, we see this out in space with comets. Here's a picture of a comet, and a comet is a ball of ice. It could be a mile or a few miles across, but it's a big ball of ice. And when it approaches, gets closer to the sun, most comets spend most of their lives in the outer solar system, way far away from the sun. But the ones that get closer to the sun, that get to where within Jupiter's orbit, certainly closer where Earth is, they sublimate. And so the solid material just becomes gas, and it becomes a tail. And we will talk more about comets when we study the solar system. We'll see a bit of them in chapter 7, and we'll study them more intensely in chapter 12. That is the end of chapter 5, part 5, Molecules and Phases of Matter. Have a great day.